ओके अच्छा, ये जो हम कर रहे हैं CFD के बारे में, मोस्ट ऑफ इट वी हैव completed already, right? Still I am doing it just because what has happened that my notes are in two different forms, right? So some things are there in the PPT in a concise form, and same thing are there in the Word document in a detailed form. So I am just switching between the two. So PPT portion we have already covered. So now we talk about this, anything which is left. So we were talking here that how we are going to come across this problem of turbulent flow. ठीक है, तो this is the solution of turbulent flow by time averaging. Okay, this is what we. So one solution available to us is RANS. We have talked about this, है ना? When we average out the Reynolds equation. Now, what does that mean? Is that you find this is the parameter, flow parameter. You take a time interval t prime or t star, which is large enough to take care of the turbulence, the variation जो random motion है, because random motions are also cyclic, right? They have different frequency, but you have taken a time frame so much that randomness is averaged out. Okay, so when you do that, your phi actually becomes phi prime, phi bar. Okay, now so then you have now three variables. One is phi bar and phi prime. We have talked about it. This is our instantaneous, this is average, and this is fluctuation. Okay, so this is what we have. Now same thing we can apply to all the variables, whether it is v vector. Okay, u is the component of velocity v, you have this. Then you can write for u, v, w, pressure and temperature. Okay, so all the variables can be written like this. Now then we talk about theorems of averaging. What does these theorems of averaging say? Okay, because we are going to come across three or four operations, right? And what we do, we take two different type variables, one is f and one is g. If we do the averaging, we will get f equal to this and g equal to this. Okay, all the variables will be in this form. Okay, and this is the fluctuation we have already talked about. This is u bar and this fluctuation is u prime. Okay, now when you do the averaging of fluctuating components, so this becomes f prime average becomes 0. That is simple, you can make out. So now what we do, the average of average component, because we will be doing this. So when we find the average of average, there are two. F is already averaged. If you find the average of that, you will get the same thing, because during that part it is constant, average is constant. That is what the function objective is, the definition is. Now what do we do? Average of a derivative, this we have talked about, but then I gave you just the solution. Now we are slightly going into deep. Now the derivative, if you are writing derivative del f by del s, and after the derivative you find the average, it can be written like this, right? Limit delta s approaches to 0, f, now these are instantaneous value, f at s plus delta s minus fs. Now what is this s delta s? Delta s is actually, you can see here, s is a general parameter and the 4 parameters x, y, z and t. So these are the actually domain, define the domain x, y, z and t. So delta s is delta x, delta y, delta z, delta t. Now these things are not changing. The flow is changing, but x is not changing. Of course, when you are talking about Einstein theory, etc., the dimension length is also changing, time is also changing. But those are cases you can talk about where you are going for very high velocities. Okay. So here when we are talking about classical mechanics, these parameters x, y, z are not changing. Okay. So now what happens is, because this s, delta s remains constant, when you take the average, this average of the whole is average of the numerator only, right? Because delta s is same during that interval. Then average of the numerator can be divided into two parts because it's a summation, right? And which means it is the derivative of the average. So now you can start from one end and you can get the average of a derivative is same as derivative of average, right? So this function is derivative of the average. Average of the derivative. So first you find the derivative, then you take the average. And this is what you first find the average, then you take the derivative. Please note that in the above derivation, delta s, delta y, delta z and delta t, they are not fluctuating. So that is why we get this derivation. Okay. When we talk about the integral, average of the integral is defined like this: integral average of the integral. So average is a summation, you can take the integral. Now when you do the integral of this, now you can do, because it's a summation, you can actually write like this. यहाँ पर ये लिखा हुआ नहीं है. This will be equal to sigma I is equal to 1 to n f delta s I and this, because it's a summation, so you can find the average of each term. Now because delta s I is constant, you can take the average of only f. What does it mean? This becomes a definition of integral of average of f. So now what you are getting, average of the integral is same as the integral of the average. Now why I am emphasizing on this is that you see that on left side you have f, on the right side you have f bar. If you are replacing left by the right, your one variable goes away, the second variable comes in. So both number of variables remain same, right? So averaging is not a problem so far. Now when you do the sum, now there are two different variables, no problem, you can do this. Again here note that on the left side you have instantaneous variable, on the right side you have average variable. But left is going, because you are replacing left by the right. So left is going, right is coming in. Number of variables remains same. Now the real problem comes here, average of the product of instant. So here what we are doing, first we are multiplying, then finding the average, right? Instantaneous. If we do that, we find the product of the variable and find the average, you actually get this, because instantaneous variable is made up of two components. Now these will give you 4 components, and finally what will happen, as I told you last time also, these two terms will go away, because average of prime is 0. Okay, now here one is average, the other is prime. So when you are finding the average, average itself is a constant and prime का average 0 हो गया, तो these two term will go away. This term will be equal to 0, this term will be equal to 0. ठीक है. Now this term does not vanish. Okay. So what you are getting is this also is written like this. Product of the two numbers, average, product of the average numbers, and you find the overall average. It is same as product of the average. So, and I have written here, this is equal to 0, this is equal to 0, but f prime g prime bar is not 0. The bar of f prime bar is 0, that is as per the definition. The average of g prime is also equal to 0, but this is not equal to 0. And the simple example you can take, if both f and g are same, you get ui, this average will never be equal to 0. Because now you don't have a negative number. U prime has both plus and minus. The second u prime also is plus and minus. When you multiply, it is all positive. So average cannot be 0. And that is why you cannot say that it's not necessary that it will be 0. Okay. Because you can't have f and g are not dependent on each other in such a way that f prime is negative, g will be positive. It's not like that. There may be cases where f prime is positive, g prime is positive, both. Or it can be a case when f prime is negative, g is also negative. So they may be correlated like this, and what you will find, they are never negative. Right? So what happens is now this is what you get, and this is the problem. Now you see, if you are replace the left side, if there is a product f and g, they are instantaneous variable. They go away and they give you 4 variables on the right side: f bar, g bar, f prime and g prime. Now you are in a soup. Your number of variables have increased. And this is the real problem with turbulence. Okay? Averaging problem. Because averaging technique यहाँ पे जाके फंस जाती है. But then they have found some via media approximations for this. It's not that they have found the actual solution. This is approximation. And what do? As Now this we have talked about, these equations. If you take this equation, continuity equation, and if you average it, what you will do? First you will do the average of the terms, then your average derivative, you will use this theorem which we have just studied. So your average will go inside, right? Average now has gone inside. Now at the moment we are assuming that it is incompressible flow, so rho bar is constant. You can take it like this. So ये आपकी equation बन जाती है, ठीक है? Okay. So this becomes your averaged equation. Now what has happened in this equation? If you look at this equation and you look at this equation, this equation and this equation. On the second equation, it is not V instantaneous, it is V bar. V instantaneous has gone. Right? So now you have an equation between average velocity. Okay? Now we take the so what you should understand is that finally what we will do, that we will replace this V bar by V normal V. So when you are talking about these equation RANS, average, Reynolds average, there they have two types of velocities and two types of parameter. One is average, the second is fluctuation, right? The instantaneous is gone, that is not taken, but we do not write average as average, we write it as V. So remember, in the RANS equation, V, when you without bar, is actually a average. It is for the sake of convenience, because the average is velocity instantaneous is never coming across, because that has been replaced between V bar and V prime. Okay. So now we come to this momentum equation. Again we are assuming that rho is constant here, and now if you see this equation, what will happen? Only this term will create a problem, because here there are two products, but we are assuming rho constant, so this will not be a problem. You will find that this average first is broken into two parts, then we use this theorem, and this average comes inside, right? Now when this average comes inside, because rho is constant, this average, U average comes. Now this is the term which has a product of V and U. Okay, on the right side all the terms have single variable, so averaging doesn't make a thing. What has happened? Your instantaneous has been replaced by average. But if you focus on this term, it's a product of two terms, and here we know all this, we have done that this product is actually equal to these two. Okay. Now then if you replace this term, you will get these two terms here. Okay. And this term comes on the right side, prime 1. Okay. Now this on the left side, you see that all these are averages. Okay. But then they are replaced by a variable without bar, the same variable without bar. So in this equation, in this equation, whatever you are seeing as U, V, etc., they are actually average velocities. Okay. But this term, these are the 9 terms which come here. Okay, they come here, and again the same thing we have written, that in this equation, you can still, we are not writing here why V is coming like that. Okay, so what it was not required to write bar here. These are the bars, we are using bars here. Okay, but you may be writing this without bars also, but it means the same thing. Okay. Now these 9 terms, these are 3 here, 3 here, and 3 here. These are called Reynolds stresses, simply because their units are stress. Okay. What are they? We don't know. It's a multiplication of two types of velocities in fluctuation in velocity in x and y direction, or any two directions. But that is stress, can't say. So it's a misnomer in a sense. They are called Reynolds. Perhaps to honor the person Reynolds who must have worked on this. I don't know exactly whether this was Reynolds' work. So this is called RANS, Reynolds average Navier-Stokes equation. So I think it is Reynolds' contribution, and to honor that they have called it Reynolds stresses. Okay. Now, so their units, we have discussed this, their units you can see, that if you multiply this rho u prime in u prime, or even rho u prime v prime, all these units will come out to be Newton per meter square. Okay. Now the same thing applies to the energy equation. Energy equation, you have this and you do the average, and here E is actually replaced by CVT. Rest all is we are doing the derivative. It's a simple, you can see. Rho we are assuming constant. Okay. So here what we do is E has been replaced by CVT. E is equal to CVT. We replace it, and in fact this CV is taken at the bottom division. We divide it. This is a way of writing it, because I told you when we were talking about generic equation, then they start meaning the same thing. Terms wise terms you can match. Okay, so that is why it doesn't make a difference whether you keep it here or you keep it there. Now this will give you three terms, because okay, if you break this term, it will have one term for the average and one for the prime, and this will give you three terms, T bar multiplied by three components of velocity. So there will be total. Now again, if you look at this equation, of course we are written bar on the left side, but the moment you are writing this term, right, so that means it is a RANS, Reynolds average Navier-Stokes equation, and all other terms are average terms, and these are fluctuating terms. Okay, so that you can make out, because in some text you might find they are putting the bar, in some text you may find that they are not putting the bar. So whether they are putting the bar or not, it is a average. In this equation which we have, either it has a average velocity or fluctuating velocity, right, whether the bar is there or not. Okay, so you can see here what we have done. We have removed the bars and we have only kept function as a without bar. Okay, so this is your prime value. Okay, now these are the three terms which you get. So now is the thing is that how do we solve this? Okay, so steps to develop Ryan's equation for turbulence. Now how the steps we follow, because what we have done so far, we have averaged the Navier-Stokes equation and got a new set of equation, but how do we solve them? In term we have added 12 more variables. Our equations have not increased, we have only added 12 more variables. Replaced instantaneous variables with average and fluctuating component. Okay, this is what we have done. So time averaging of Navier-Stokes equation generate 12 unknowns. 9 are this and 3 are this. Okay, now 9 of these unknowns when multiplied by rho, they give units of shear stress, and therefore they are called Reynolds stresses. That is okay. Okay, now these 9 unknowns are written in terms of 2 unknowns. Now this is what they are doing the trick. We are converting all these 9 unknowns into 2, and what are those? This has been done by Buzinex, 1868. Count the number of years. We are almost 200 years. 175 you can say. All this existed 175 years before. Okay, so propose that Reynolds stresses could be linked to the mean rate of deformation. So what he is saying, that this variable we can convert this into average. So what he is doing, he is correlating the fluctuation with the average velocities, and then he has written that okay, if you have this stress and where I In this case, I, both are I and j. In the second equation, you will find it is I and j. So when I and j are not same, here in this equation, when I and j are same, so that means when you are multiplying u prime with u prime, v prime with v prime, and w prime with w prime. So this is talking about these 3, and this is talking about 6, so total 9. Okay, so that what it is saying is that this जो फंक्शन है, एवरेज वेलोसिटी में जो ग्रेडियंट है उससे कोरिलेट किया फ्लक्चुएटिंग वेलोसिटी को, और उसमें म्यू टी ऐड कर दिया. म्यू टी इज द टर्बुलेंट विस्कोसिटी. ओके, एंड दिस इज अ टर्बुलेंट काइनेटिक एनर्जी. सो उसने उसको टर्बुलेंट काइनेटिक एनर्जी से भी जोड़ दिया है. ठीक है, वी विल टॉक अबाउट व्हाट इज टर्बुलेंट काइनेटिक एनर्जी. सो इट इज़ द फ्लक्चुएटिंग वेलोसिटी, उसका जो स्क्वायर करके ऐड करते हैं, देन यू विल गेट द turbulent kinetic. We will do it what it is. Now when you are talking about this variable where I and j are not same, where I and j are not same, then it is a summation of the two. Rate of change of velocity, average velocity with respect to the other coordinate. So u with y and v with v with x. So this type of variation is there. So and what you are seeing here, primes are being replaced by average. Okay, so what in turn is saying that fluctuation in a flow in the velocity can be related to its average gradient of average velocity, right? And this is a proposition. There is no proof for this. Okay, there might be some a close proof, like empirical formula may be there, something like might be there ki, but exact is not there for this. Okay, now what is mu t? Mu t is called turbulent. It has 3 names: turbulent viscosity or eddy viscosity. Eddy means it is rotating, right? Turbulent is slightly, eddy is slightly different from turbulence, but you can take both of them are same, because eddies actually create turbulence. And this is also called turbulent momentum diffusivity, because this function is telling you how the turbulence is diffusing. Is something like k, not this k, the thermal you have in Fourier equation. K is a basically thermal diffusivity, how the heat is flowing, panning out. Here how the momentum is panning out, distributing, that is, and k is turbulent kinetic energy. So what has actually is done, he has converted 9 variables into 2, because u prime average velocities were already being used. They are not the new one, they are the existing one. What are the new ones? Mu t and epsilon. So 9 variables have been replaced by 2. Okay, then these are the 3 more variables which are multiplication with temperature. What do we do about that? Then he says that as per Boussinesq, since diffusion of momentum and heat in a turbulent flow follow the same mechanism of eddy mixing. Now he is again proposing. What he is saying is, the way the turbulent momentum in a turbulent flow, the way the momentum is diffusing, the same way the thermal energy is diffusing. Because whatever mass is diffusing, that itself is carrying momentum as well as thermal energy. So they are following the same thing. Okay, so he says that turbulent transport of temperature is taken as proportional to the gradient of mean value of the transported quantity. So what he is saying is same thing. Now he says I can replace by this turbulent thermal diffusivity. Again what it is doing, he is converting the prime variables, 3 variables, into the average one. Okay. Now there is one more variable, now it has been added. So currently 12 has been replaced, and what you have got? Mu t, epsilon and gamma t. You have this turbulent diffusivity, and this will be epsilon will be dissipation, K, sorry, we have K here, turbulent kinetic energy and thermal diffusivity. We have come to from 12 to 3. Now what he is saying is that, like Prandtl number for laminar flow, for turbulent Prandtl number is defined as like this: the ratio of, there the Prandtl number was mu by K, here it is mu t by gamma t. Okay. And then he says that, however, since the turbulent transport momentum and heat is due to the same mechanism of eddy mixing, value of turbulent diffusivity can be taken to close to the turbulent viscosity. He is saying both are same, and you will find that what he says, that these two are same. So now what he has done, he has replaced this by this, which was already existing. So we have come to 2 variables. So from 12 we have come to 2. Okay. Now thus we have replaced gamma t by mu t. Okay. And what he also mentioned, that experiments have established that this ratio is often nearly constant. Most of the CFD procedures assume that this is to be the case when Prandtl number, turbulent Prandtl number equal to 1. And it is not same for the laminar flow. Their Prandtl number for air is 0.7 or something like that, right? But here it is taken as 1, and experiments have shown that it is so. Okay. Now what happens is, after the above approximation, we have effectively replaced 12 unknowns with 2 parameters K and mu t. K is turbulent kinetic energy here, and mu t is turbulent diffusivity, momentum diffusivity. Okay. Now what he is saying, we further replace mu t by epsilon. We are going to replace this. Why? It is basically just a way of writing. It was not necessary to replace. So finally you are getting what? K epsilon, and this is your 2 equation K epsilon model. This is where we are going. Okay. There is a model called K epsilon, or 2 equation K epsilon model, which is quite popular. Now mu t has been defined like this, where you have C, the thermal capacity, mu kinematic viscosity, rho is density. Now these are all properties of the fluid. So there is nothing like that. It's basically all these above are constant except that rho, which is changing. Again it is a property of the fluid. So all the properties of the fluid have been used to convert mu t into epsilon. So you have just replaced them. Okay. Thus finally we have only 2 unknowns, which are K and epsilon. So there are only 2 unknowns are left. Now what is K? K is the turbulent kinetic energy, and it is written like this. So you have prime velocities, you make square of that and you add up. So over the average flow, whatever the fluctuation is, the kinetic energy carried by that fluctuation, you take it as the turbulent kinetic energy. So this will be actually u prime square plus v prime square plus w prime square, and addition of that. Okay. And this is epsilon is called dissipation rate of turbulent kinetic energy. Now, so on one side turbulent kinetic energy is being created. This is what is happening in turbulence. On one side randomness is being generated, on the other side it is being mixed, it is diffusing, it is you can say due to viscosity it is getting converted into normal flow. Okay, so this is epsilon is defined as here where nu t is equal to this. So this is another way of defining this. Now why he has done all that is a deep exercise. We will not go into deep. What my purpose in telling here is that this is a model which is based on assumptions, and this is how we proceed. Okay. And the problem with averaging we have to. Now this two equation model epsilon and k are obtained separately. Now the equation. Now then he has given equation for epsilon and k also, because you have got two extra unknowns. So you require two more equations. So this model actually what it does, defines k and epsilon is okay. It gives two equations for epsilon and k. One for epsilon, one for k, and they may be coupled, and they are quite complicated. I couldn't understand that how to solve it, and I thought it is we are going, because I have to actually communicate it to you. That is an issue, and then whether we'll be using it or not. So I rather wanted to give you a brief introduction to it instead of going deep into it. So these two equations are added, and that is why it is called two equation model k epsilon. Okay? Now we'll take another 5 minutes or so, finish it off. You have class? So viscosity, what is viscosity? It is the resistance. We know about the viscosity. So there are two types of viscosity. You have this definition of viscosity. The only difference is one is a laminar viscosity, the other is a turbulent viscosity. Okay, and you can see that. And viscosity defined for turbulent flow is differentiated as, so when there are turbulent flows, the viscosity you are talking about is a turbulent viscosity, and otherwise you talk about laminar viscosity. And in laminar viscosity, momentum transfer occurs due to random motion of molecules. We have talked about it. The dissipation is occurring at the level of molecules in a laminar flow, while in case of turbulent viscosity, the momentum transfers occurs due to eddies or parcel of fluid. So there is a group of molecules which move from one place to another place, and they distribute the momentum as well as energy. But there is one more thing, that the final mixing is through molecular diffusion. So this you should remember. So turbulent diffusion in itself is not a complete process. As I gave you the example last time, that you are putting water, spraying water on a field. Now you are throwing water at different points like a sprayer, water sprayer. So the drops are falling at different place. So in a way what you have done, you have speeded up the process of mixing. But after that, when the drop falls at a particular place, it diffuses into that point and mixes up, right? Same thing we talked about, in a liquid you put some particles, so you churn it. So the first thing what you are doing is, you are basically distributing the particles all around. Now wherever they are, they start dissolving. That is a molecular diffusion, and then it becomes uniform. Okay, so this is the thing. And what is this turbulent kinetic energy? You can see that this is how we defined it. This is called specific turbulent kinetic energy because this is per unit mass. Okay, so nothing special about it. If you want to talk about total kinetic energy, you will have to multiply by instantaneous. Now these are instantaneous velocities, not average one. These are instantaneous. So if you square up the instantaneous velocity, you will get total kinetic energy. Now what you can do, if you want to find the now you find the average of this instantaneous kinetic energy, you will again have to do this exercise. This is instantaneous, you find break it up into two parts, average plus random fluctuating, and take the average. You will get finally these two components are left, okay, and you can again do the average of this and this. So it is having two components, one is this, one is this. So this is the kinetic energy based on instantaneous velocity. This is the kinetic energy based on average velocity, and this is the kinetic energy based on random. This is your turbulent kinetic energy. Okay? So you can say turbulent kinetic energy is total kinetic energy minus kinetic energy based on average velocities will be equal to turbulent kinetic energy, right? And this is based on average over time. This is the average kinetic energy, okay, and this is the same thing. So thus the turbulent kinetic energy represents the difference between the total kinetic energy of a cell and kinetic energy of the cell based on the flow velocity average over time. So you have three components. Total kinetic energy is equal to average plus fluctuating. So you can find any one of them. You can say total kinetic energy is equal to average kinetic energy plus random kinetic energy or turbulent kinetic energy. Okay? Now then what is the dissipation? Dissipation rate of turbulent kinetic energy is defined like this, and that is why epsilon has come. It is basically dissipation rate, okay, and you define it like this. You can replace this we have seen before, okay, and the units of this is again specific kinetic energy per second. So epsilon is telling you what is the rate at which your random kinetic energy is dissipating, right? So these two things become important. Now, so this we have talked about. I'll just briefly go through this. So how finally we are resolving the turbulence is we are तो first thing is that reducing the size of the cell, which is not a proper solution because we cannot reduce much. That from where we started, reduce the size of the cell, reduce the time step. That is not possible. So what we do, averaging. Okay, when you do the averaging, it leads to generation of unknowns which are called Reynolds stresses. And now it says that there are no laws available to account for Reynolds stresses. There is no such thing available. Okay? As a result, some empirical equations are generated to solve the system of equation. So these empirical relations are based on hunch feeling, theory, mix of theory, experiment, etc., etc., etc. Okay. This approximation introduces an element of uncertainty in the solution, and we are never sure that the solution of the turbulent flow is accurate, because model itself is approximation, it's an assumption. Okay, Now, this problem is resolved to an extent by validating the CFD formulation, and that is why you do the validation, so that to an extent you are through it. Now, then what is this two equation model? This is what we have talked about. Okay? Same thing, 12 variables reduced into two variables, epsilon and k. One is kinetic energy, second is dissipation rate of kinetic energy. Okay, and the important point to be noted that two empirical equations are written to take care of these two unknowns. This is called a two-point closure scheme two-equation model. Right? Because you have to have the same number of equations as the number of unknowns. So you create those two equations. Okay. Then you have other option available to you is LES, in which what you do, you reduce slightly the size of the grid. So in a way, the larger eddies are broken up in the grid and you can capture them, but not all of them. So what you are doing is now you are basically part of the turbulence you are covering with CFD and regular process, the other part you are doing with approximation, averaging. In DNS, what you do, you go still further and you take all the things. But now because you have increased the number of cells and increased the number of time steps, you have to reduce the domain. So what the thing is, you actually, what you do, you can solve. So DNS solutions exist, theory exists, formulation exists. The problem is the size of the problem. You can discuss and the time it will take. Right? So smaller problems simulated for a longer time, you may be able to solve with DNS. And now the people are hoping that the computer speed will increase. Either some other mathematics things should come, which should be able to predict the turbulent flow. Right? If you are able to capture the origin and dissipation of turbulent flow, then it becomes part of the equation. Then it is fine. You will be able to solve it. Right? Otherwise, what you are doing, you are going smaller and smaller and smaller, with which you are trying to solve it. So as the computers, the CFD is going to be most benefited by the quantum computers. You are going to get a better and better solutions. Okay, so this is the end of the CFD, turbulence, what I wanted to talk about. Just another 1 minute. So far what we have done, we have talked about only equations. And equation in differential form, which cannot be solved on computer directly. Okay. The next stage is to convert those differential equation into algebraic equation. Once we learn that technique, that how we do it, right? Again, there are challenges there, but we will do basic theory of it. Once we have done that, then we have to see how do we find the solution using computer of those equations. Because remember, those equations you have, suppose you have 10 equations or maybe 7 or 8 equations to solve. For each cell you have to solve those 7 equations, and we are talking in terms of 1 million cells, that order. That means 7 million simultaneous equation solution. How do we handle that problem? Because that cannot be done normally with the computer. You have that Gauss elimination method by which you can solve the equation n number of equation, n number of solution unknowns, you can solve it. But that n is very small, 10, 15, and the computer starts heating up. Right? We are talking about 10 million. How do we handle it? That is the challenge. Okay. So we stop here.